I would like to start this afternoon session and welcome everyone who has joined us here. My name is Claudia Draxl. I have the pleasure to chair this session and also spend a few minutes to give you an overview of my, I would say, personal view on where the field is that we're talking about. And in that sense, I have prepared just a few slides to introduce the topic of experimental and hybrid databases. So we have seen already a few talks on these topics in the morning session, but we're going to have a few more in this afternoon. And as I said, I'd like to give you my personal summary about where we are in this field. So the first question is, of course, is why do we need databases in experimental or in material science in general? And I think the answer is pretty clear. Materials are everywhere, anywhere in our society. Whatever we touch or we do, we're somehow concerned with materials. And it's also clear that we need to get better and we need to get faster to the market in order to solve our issues that we have in terms of energy, environment, and other things. So the question is, how do we approach this? And I think a very typical and very popular approach is high throughput screening. So again, we had already some examples in the morning. High throughput screening applies to both theory and experiment. Maybe it started in experiment actually, but maybe it's more popular in theory because we can dream up any material on the computer and see what comes out and what the properties are. But in particular, experimental high throughput screening is getting more and more popular as well. So the idea is that you define the properties you're interested in, and then you take as many materials you like, and then you see where you get in this funnel, whether these materials fulfill these properties or whether they drop out somewhere. So, and of course, this creates a lot of materials, either by synthesis or by experimental or by theoretical investigations. And these are typically harvested then in databases, or the information about that. So in that sense, if you combine this why and this how, then we see that databases are very often established in connection to high throughput screening. Other databases are established because laboratories like to organize their own data. Or a third category could be that research groups do this effort just for their own research, to get organized and also to harvest the data that they have, or it simply could be a combination of all of this. Right? So going beyond why and how, what does this mean now for our field? So that means that we have probably a lot of databases that serve different purposes depending on who was behind and what the purpose was of starting high throughput screening or work in the group. Many of such databases exist. They're very big ones. They're well known. Not so many, in fact, in experiment, because many of these experimental databases are not open or probably not yet open. So I'm aware of quite a few who are right now established but are not open to the public yet. And most of them don't accept data from outside. So I think it's pretty human that people like to stay in their realm, because if you accept data from outside, then you have to live a lot of uncertainties and issues that I'm going to address in the next 2-3 minutes. So, in fact, what are crucial issues for maximizing the benefits of databases? And I like to address two examples here. One is metadata. So the description of data, without no doubt, is crucial in order to exploit data properly. And very often these metadata are either not defined or they are lost. So additional information is lost. So just think about, you perform an experiment, then you may take down some notes on under which conditions this experiment has been taken, or likewise this applies also to the synthesis of samples or to the to building an apparatus. Very often also there are failures, so the results are not as expected, so this goes automatically away. But at the end of such an investigation, typically a paper is published, but whatever has been taken down aside is typically forgotten. So this goes to the trash. And in fact, I think there are many data around on this globe where people keep the data because data need to be kept, because the funding agency, for instance, tells to do so. But maybe these data are of little value if they're not properly annotated. So it's crucially important that all this data that are stored somewhere are indeed very well characterized by metadata. So this is a very big issue, and this is a lot of work if you want to do it properly. The other issue concerns fairness, and this in particular the I in FAIR. So the interoperability is a particular issue, and I always show the same example, but I think it's really striking. So this is the optical spectra of silver, right? So silver is a very simple material, just has one atom in the unit cell. It's a noble metal, so it should behave in a noble way, put it like this. But if you look at this spectra, you can't understand that they obviously all refer to the same material, because in the ideal world, if 1,000 people measure the same thing on the same material, you should get 1,000 times the same measurement. And this is definitely not the case. So it's not only that the intensities, the magnitude is very different between different experiments, but also the peak positions, they're off by not only milli-electron volts, so tenths of an electron volt, but even electron volts. So obviously, either we don't deal with the same material, that means the sample quality and is crucially important, or the measurement has been taken under different conditions. And so overall, if we look into such data, we realize that there is a lot of veracity, so uncertainty in this data. And this uncertainty may come from, let's say, the sample quality, the way we measure, for instance, under UHV conditions or not, is the contamination or the defects inside. But there's also something that is known as the term variety in the 4V of big data. And in this case, variety means that you can measure the same thing with different means. So for instance, for getting the dielectric function that is proposed here, you can use ellipsometry, absorption reflectance spectroscopy, or even electron loss spectroscopy. Interestingly, none of these probes gives you this property directly, so there's always transformation steps involved, and that's why this not only adds to variety, but again to veracity, to the uncertainty in data. And also, there's needless to say that you can also compute this on many different levels. So now, if you go back to our databases, what are the pros and the cons? What we can learn from this in relation to what we have heard before. So if we just consider high throughput databases, then data are typically homogeneous because all data have been taken under the same conditions or have been computed with the same computational means. So there is no issue of interoperability. However, metadata still are crucial, and but the owners of these databases, they are very free to define file formats and metadata according to their wishes and according to their needs. That's one thing. However, if you like to bring data together from different sources, this starts to become a burden. So different data from different sources, of course, are great because this allows us to go beyond the individual goals. So we can screen a large margin material space and employ artificial intelligence techniques. But for this, we need to make sure that data interoperable. So in that sense, this highlights the needs for common standards for file formats and definitions of metadata, or we need to convert them from one database to the other, which is probably the more practical thing. And we also need to assess data quality, otherwise we would compare apples and pears if we bring together data from different sources. So, and this brings me now to our program. I have mentioned before that databases are created under different conditions, and our speakers reflect these different situations, I think, very well. So we have Christoph Koch, Volker Blum, and Andrei Zakudayev. And I start with the latest one, and the last one in the program, Andrei Zakudayev from NREL. He is one of the proponents, or a big key person behind the high-throughput experimental database that's built up and hosted by NREL, so probably for the purpose of getting the data organized in their own lab, but of course also to find materials for certain purposes. A different situation, I guess Volker Blum is going to talk about. He is one of the persons behind Hybrid 3. And Hybrid is really a hybrid database, so it not only hosts experimental data, but also theoretical data and also data from literature. So I'm also curious what we hear about this. I'm not going to tell more because this is the topic of the talk anyway. And last but not least, Christoph Koch, who is not establishing a database by himself, but he is more about verification of a certain instrument or a certain technique, which is electron microscopy in this case. And he's one of the first persons to add experimental data to the NOMAD database that so far has been a theoretical database.